Let's talk about randomness. We think we know what it is. A coin flip. A roll of the dice. Shuffling a deck of cards. It's the stuff that happens without a plan. It's unpredictable. It's the opposite of a pattern. Our brains are built to find patterns, so we can't find one, we call it random. But what happens when you ask a computer to be random? What happens when you ask a machine, an entity built entirely on logic and rules, to do something that has no rules? This is where the question gets tricky. Can an algorithm, a set of instructions, a recipe followed by a computer, ever be truly random? The short answer is no. And the long answer is what this is all about. It's a story that touches on everything from video games and lottery tickets to the secrets of the universe and the nature of reality itself. First, we need to be clear about what a computer is. A computer is a deterministic machine. That word, deterministic, is key. It means that if you give it the same input, it will follow the exact same steps and produce the exact same output every single time. There is no guesswork. There is no improvisation. It's a perfect, relentless follower of instructions. Think of a simple calculator. If you type 2 plus 2 and press enter, it will always give you 4. It will never give you 5 on a Tuesday or 3.14 when it's feeling creative. It follows a precise algorithm for addition. An algorithm is just that, a recipe, a set of steps to get from a starting point to an end point. Now, imagine you ask this machine for a random number. How would it even begin? Where would it look for this randomness? Inside its own circuits, everything is orderly. Everything is a 1 or a 0, a switch that is on or off. There's no chaos in there, no spontaneity. So when you ask a program for a random number, it has to cheat. It has to create an illusion of randomness. This illusion is called pseudorandomness. The prefix pseudo means fake or false, so a pseudorandom number is a fake random number. It looks random, it feels random. If you test it statistically, it passes all the tests for randomness. But it isn't. Underneath the surface, there's a hidden pattern. There's a deterministic algorithm working away, just like the algorithm for 2 plus 2. Here's how most pseudorandom number generators, or PRNGs, work. They start with a number. This initial number is called the seed. The seed is the secret ingredient. The algorithm takes this seed and performs a series of mathematical operations on it. But it might multiply it by a huge number, add another number, and then take the remainder after dividing by a third number. The result is your first random number, but it doesn't stop there. To get the next random number in the sequence, the algorithm uses the number it just generated as the new input. It performs the same mathematical operations on it, and out pops the second random number. And so on, and so on. It's a chain reaction. Each number is born from the one that came before it. It's like a line of dominoes. The first domino is the seed. Once you push it, the entire sequence is set in motion. You can predict exactly how every other domino will fall. It looks chaotic for a moment, but the outcome was determined the instant you push that first one. This is the secret weakness of all pseudorandomness. If you know the algorithm and you know the seed, you can predict the entire sequence of random numbers. Every single one, from the first to the millionth. It's not random at all. It's just a very long, very complicated pattern that is hard for a human to spot. So, where does the seed come from? Often, a program will try to find a seemingly random seed to start with. A common trick is to use the current time, down to the millisecond. When you start a program, it grabs the system clock's value. That number, like 1,678,886,400,123, becomes the seed. It feels random because you're unlikely to start the program at the exact same millisecond twice. But even this isn't perfect. If you could start two computers at the exact same millisecond, running the same program with the same PRNG algorithm, they would produce the exact same sequence of random numbers. This is actually a feature, not always a bug. In scientific simulations or video games, you might want to reproduce a specific random event. For example, the developers of the game Minecraft use this idea. If you type in a specific seed when starting a new world, it will generate the exact same landscape of mountains, rivers, and caves every time because the algorithm for world generation is using that seed as its starting point. It feels random and unique, but it's perfectly repeatable. For most things, this fake randomness is good enough. When you play a video game and an enemy drops a random item, it's a pseudo-random number that decides it. When you shuffle a playlist on a music app, it's a pseudo-random algorithm arranging the songs. For these applications, all you need is something that appears unpredictable to a human. the stakes are low. But sometimes, good enough is not good enough. The most important area where pseudorandomness fails is cryptography. Where cryptography is the science of secure communication. It's what protects your credit card number when you buy something online, what secures your bank account, and what keeps your private messages private. Modern cryptography relies heavily on random numbers. These numbers are used to generate the secret keys that encrypt and decrypt information. If your key is predictable, your entire security system falls apart. Imagine an attacker who wants to read your encrypted messages. If they know you are using a standard pseudorandom number generator and they can somehow guess or figure out the seed you used, they can generate the exact same random key you did. And just like that, all your secrets are exposed. This isn't just a theoretical problem. There have been real-world security breaches because of weak or improperly seeded PRNGs. A classic example was an early version of the Netscape web browser. Its encryption was flawed because it used a seed that was too easy to guess. The seed was based on the time, plus a couple of other system variables. Researchers showed that by monitoring a computer's network traffic, they could narrow down the possibilities and guess the seed in a matter of seconds, allowing them to break the secure connection. This is where the hunt for true randomness begins. If algorithms can't do it, if the world of pure logic and mathematics is fundamentally predictable, where do we turn? We have to turn to the physical world. The universe around us is filled with processes that are, as far as we can tell, genuinely unpredictable. This leads us to the other kind of random number generator, the true random number generator, TRN, sometimes called a hardware random number generator, HARNG. Unlike a PRNG, which uses a mathematical formula, a Trong harvests randomness from the real world. It has a sensor, something that can listen to the chaotic noise of the universe. What kind of noise? One of the earliest sources was atmospheric noise. The crackle and hiss you hear on an AM radio between stations isn't empty space. It's the sound of distant lightning strikes from all over the world, cosmic radiation, and other unpredictable electromagnetic phenomena. A TRN can have a radio receiver that digitizes the static, turning the unpredictable crackles into a stream of ones and zeros. Since no one can predict the next lightning strike in a thunderstorm 1,000 miles away, the resulting numbers are truly random. Another classic source is radioactive decay. The atoms of a radioactive element, like americium, decay over time. But you can never predict exactly when a specific atom will decay. It's a fundamentally probabilistic event. You can know that over a certain period about half the atoms will decay, but that's the half-life, but the exact moment for any single atom is unknowable. HRNG can use a Geiger counter to detect the particles emitted during decay. The time between each click is random. By measuring these tiny, unpredictable intervals, you can generate a stream of truly random numbers. Modern computers have their own sources of physical noise. The electronic components themselves generate tiny, random fluctuations. For example, the thermal noise in a resistor caused by the chaotic jiggling of electrons due to heat can be measured. The exact voltage at any given microsecond is unpredictable. Intel and AMD have built TRNGs directly onto their processor chips that use this kind of electronic noise to generate random numbers for cryptographic tasks. One of the most famous and visually interesting examples comes from the company Cloudflare, which helps secure a large portion of the internet. In their San Francisco office, they have a wall of lava lamps. A camera is pointed at the wall, constantly taking pictures of the slowly moving, unpredictable blobs of wax inside the lamps. The image data from the camera, the exact color and position of millions of pixels, is constantly changing in a way that is chaotic and non-deterministic. This data is then processed and hashed to produce a stream of high-quality, truly random bits. They also combine this with data from other random sources, like a machine that measures the decay of a pellet of uranium. The ultimate source of true randomness, however, seems to come from the deepest level of reality we know, quantum mechanics. In the world of classical physics, the world of Newton, everything was seen as a giant clockwork machine. If you could know the exact position and momentum of every particle in the universe, you could, in theory, predict the entire future. This idea is often called Laplace's demon, a hypothetical intelligence that could see the entire past and future just by knowing the present state of everything. In a clockwork universe, there is no true randomness. There is only complexity that we are too ignorant to understand. But in the early 20th century, quantum mechanics shattered this deterministic view. At the subatomic level, the universe seems to operate on pure chance. You cannot know both the exact position and the exact momentum of a particle like an electron at the same time. This is the Heisenberg uncertainty principle. The more you know about one, the less you know about the other. More than that, the behavior of a quantum particle is described by a wave of probability. Before you measure it, a particle doesn't have a definite state, it exists in a superposition of all possible states. When you measure it, this wave collapses into one definite outcome, and the specific outcome it chooses is, according to the standard interpretation of quantum mechanics, fundamentally random. Albert Einstein famously hated this idea, stating God does not play dice with the universe. But a century of experiments has confirmed that, at its core, the universe does seem to play dice. This quantum randomness is the gold standard. Companies now build quantum random number generators. These devices might work by firing a single photon at a semi-transparent mirror. The photon has a 50-50 chance of passing through the mirror or being reflected. Whether it does one or the other is a true quantum coin flip. And a detector on each side of the mirror registers the outcome. If it passes through, that's a 1. If it's reflected, that's a 0. By doing this millions of times a second, you can generate a stream of bits that is as random as the laws of physics currently allow. So, we have two distinct worlds of randomness: the fake algorithmic deterministic world of pseudorandomness, and the real physical probabilistic world of true randomness. Does this distinction actually matter for most of us? If you're designing a casino's online slot machine or a national lottery system, it matters immensely. The public needs to trust that the outcome is fair and unpredictable. Regulators often mandate the use of hardware-based, true random number generators for these applications. You can't have a system where a clever hacker could figure out the seed and predict the next winning lottery numbers. If you are a scientist running a complex simulation of climate change or galaxy formation, you might actually prefer pseudorandomness. Why? Because you want your experiment to be repeatable. You can run the simulation once with a specific seed, record the results, change a variable, and then run it again with the exact same seed to see how the change affected the outcome. The random events in the simulation will be identical in both runs, which is exactly what you need to isolate the effect of the variable you are testing. True randomness would make it impossible to perfectly replicate an experiment. If you're a digital artist creating generative art, where an algorithm creates a unique image or piece of music, the line gets blurry. Does the art need to be based on true randomness from a quantum source? Or is the complexity of a good prung enough to create something that feels new and surprising? For the aesthetic experience, pseudo-randomness is almost certainly sufficient. The goal isn't unpredictability for security, it's unpredictability for novelty. But the question goes deeper than just practical applications. It forces us to confront the nature of order and chaos, both in our machines and in our universe. The very idea of an algorithm is to impose order. It's a human-made construct designed to take messy inputs and produce clean, predictable outputs. To ask an algorithm to be random is to ask it to betray its own nature. It can wear a mask of chaos, it can generate sequences so long and complex that they are indistinguishable from true randomness for all practical purposes, but it can never escape the fact that it started from a seed and followed a path that was laid out from the very beginning. This leads to a fascinating philosophical thought. What if our universe itself is just an incredibly complex algorithm running on some kind of cosmic computer? This is the clockwork universe idea, updated for the digital age. In this view, the randomness we see in a coin flip isn't truly random. It's just the result of a system so complex, the force of your thumb, the air currents, the microscopic imperfections on the coin, and the table map moron, that it's impossible for us to predict. The outcome was determined from the start, we just lack the information to see it. If this were true, then only quantum events would be a potential source of true randomness. But what if even quantum mechanics isn't the final story? Some physicists, though they are in the minority, speculate about hidden variables, unknown properties, or rules that determine the outcome of quantum events. If such variables exist, then even a quantum coin flip isn't truly random. It just appears that way because we don't know the hidden rules. If that were the case, then perhaps nothing in the universe is truly random. Everything, from the decay of an atom to the formation of a thought in your brain, would be part of a vast, deterministic chain of cause and effect. This brings us to the human mind. Are we any different from a computer? Our brains are made of neurons firing in complex patterns. These are physical processes governed by chemistry and electricity. Is a thought that pops into your head a truly random event, or is it the predetermined outcome of a chain of neural firings that began long before you were aware of it? The question of whether an algorithm can be random is, in a way, a reflection of the ancient debate over free will versus determinism. Are we the authors of our own thoughts, or are we simply complex machines running a biological algorithm, with our sense of freedom being just a convincing illusion? The pursuit of randomness has taken us from a simple computer command to the very edge of physics and philosophy. We've seen that the machine, in its pristine world of logic, cannot create chaos. It can only mimic it. To find real unpredictability, we have to look outside the algorithm into the messy, noisy, and perhaps fundamentally probabilistic reality we inhabit. An algorithm is a map. It shows you exactly how to get from point A to point B. It can be a very complicated map, with thousands of twists and turns, so many that it feels like you're wandering without a path. But the path is always there. True randomness is the uncharted wilderness. There is no map. There is no path. Each step is a fresh event, unconnected to the one before it, with an outcome that is not just unknown, but unknowable until the moment it happens. So, can an algorithm be truly random? No. By its very definition, it is a system of order. And while it can be an incredible actor putting on a masterful performance of chaos, it can never escape the script it was given at the start. The true, raw, untamed randomness belongs not to the world of algorithms, but to the universe itself. And our ability to tap into that cosmic noise, to listen to the dice rolls of reality, is what bridges the gap between the predictable world of the machine and the wild, uncertain world we all live in.